Hi, and welcome to the next section on evaluation for ML models, which is on the very fundamental definition of the generalization error of a machine learning model and of a machine learning learning algorithm. So our learning goals for this section are to understand the general goal of performance estimation and to connect this to the formal definition of generalization error as a proper statistical estimator of future performance. We'll understand that there is unfortunately a subtle difference between, or at least a difference in terms of its formal definition between the generalization error for a given fixed model and the generalization error of a learning algorithm. And unfortunately, we'll have to resort to the later in many practical situations because if we are fitting a machine learning model on a data set, we'll usually fit that on the total complete data set, and then no data will be left for proper untouched test data evaluation, which we usually have to use in constructing practical, reliable estimators in machine learning. And we'll also discuss the difference between outer and inner loss functions, where the latter are used in empirical risk minimization and the former are used in black boxy performance evaluation from the outside and are also called performance metrics. Basically, in the whole chapter, study the question how to properly statistically characterize and estimate a learning algorithm's or a model's future performance. So remember how the training of a machine learning model worked through empirical risk minimization. We are given a certain training data set, and unfortunately, usually that data set will be the complete data set that is available to us. So we will work on that data set, run our empirical risk minimization algorithm associated to our hypothesis space on that training data set, perform risk minimization of our given loss function for our given hypothesis space, and that will result in our optimal model f hat or its associated parameterization vector theta hat. Of course, there will also be an associated optimal empirical risk value, so kind of the minimal value of this guy here. And of course, it now seems very attractive to simply report this minimal empirical risk value as an estimator for future performance. Unfortunately, and as we have already seen before, and as we'll discuss here in this chapter again, discuss again and again also in later chapters, overfitting can happen in machine learning. And because overfitting can happen, this inner risk minimization value, or we will also later call this the training error, is usually strongly optimistically biased. So it will be much lower and it will look much better than the true future performance of our minimal model from this ERM workflow principle here. As I said, we'll study this more in depth later in the section on the training error. What I want to do here now together with you is I want to first of all define the fundamental concept of the generalization error as an expected loss over untouched, unseen test data from the same data generating process that our training data comes from. And to practically estimate this, we really need independent, unseen test data. There will be a separate section on that as well, but let's assume that here for a given that we should really do that. And I hope that makes intuitive sense, right? That we should really simulate what happens in practice during the application of a model anyway. So if we're going to use our model and apply that, we're not going to predict on the data that we have used during the fitting process. We'll predict on new data that nonetheless comes from the same distribution. That's what we can assume, that this will be an IID sample from the same distribution, but we will not assume that this is a direct copy of an observation that we have seen during training. Now, the first thing we can now do mathematically is define this generalization error for a fixed given model. And this is really easy. So I'll define this term here, the GE of a given fixed model f hat for a certain loss function L. And we'll discuss a little bit later that this loss function here could be in principle something else than what we have used for fitting f hat. And this is now simply the expected loss when we apply that model to fresh test samples X and Y, which come from the same distribution. So this expectation here is simply an expectation over this random vector, or this random tuple X and Y, which is a sample from this data generating process, capital P. So our sampler for our complete labeled data. And everything else in this definition here is basically constant. Especially this f hat is constant, this is given, and this L is some loss function that we're also given. We can also easily construct an estimator for that guy here if a dedicated test set is available to us. So let's assume that a new independent test set is available to us that we haven't used for fitting our model f hat, and that this test set is of some arbitrary size m. So of course, what we now can do is we can simply evaluate this expectation here through, I don't know, if you want to use a fancy term for this, Monte Carlo integration. So we'll simply iterate over the test set, compute the predictions, compute all of the losses, sum them all up, average them, and we are done. So this is really easy. Problem with this is very often we can't really exactly apply this in practice because no really dedicated test set is available to us. So in general, we'll just be given a single data set, and at the end of our fitting process, we'll fit our model on that complete data set, and then there is no dedicated test set. There is no data left to us to exactly directly apply what I've just described here. So this model f hat is usually fitted on the complete data set, and then zero data is left for us. And I'll discuss this a little bit more in a few seconds. Before we are going to do that, let's assume that this is possible. Let's simply visualize this a little bit and familiarize us a little bit more with that concept. So here I'll now study the test loss basically as a random variable from which we will then later on take the expectation. So I'll simply have a look at this guy here as a random variable in terms of X and Y, without taking the expectation immediately. I'll simply take a toy example here, a toy data set, the Friedman 1 test problem. That's a regression problem, I think if I remember correctly, a 10D input problem. I'll simply pick a linear model, but that really doesn't matter for this example here. So some machine learning model. I'll fix a training set size of 500, and on these 500 observations, I'll fit my fixed model f hat and store that. And this is not stochastic for me now. This is constant. I'll kind of condition on that now. And I will now feed 5,000, or you could say an infinite amount of fresh test data points to that model and plot all of the point-wise losses. And in this instance here, because this is regression and because this is kind of my default choice, I'll use the L2 loss, but I could have used something else. And then I will simply plot these, the distribution, the density of these point-wise L2 losses. You can see them down here. So this is kind of a unimodal distribution with quite long tails. I've actually clipped them off here on the left-hand side because the curve was actually going on for quite some more. And I've also marked the mean, and actually not one standard deviation, simply the mean of the density of the distribution here. And this is exactly what we would now compute with this expected value. Or you could also say we are now computing this empirical estimator here. Now, few extra comments on inner and outer losses. I've already said that sometimes we would like to evaluate our learner actually with a different loss function or a different loss metric than what we would have used, than what we had used during training. So the usual terminology for that is what we are using during empirical risk minimization we'll call the inner loss, and what we are going to use during evaluation time we'll usually call the outer loss function, simply to distinguish between the two guys, the inner L function and the outer L function. And we'll use these different losses usually, if it's computationally advantageous to us, to deviate from the outer loss, which is usually dictated by the application at hand. So usually we have some application in mind to construct our predictive model for, and that usually dictates also to us how we should evaluate that predictive model. but sometimes that loss function is really not so great for optimizing. This could be, I don't know, some kind of a weird loss function, which is non-differentiable or not even continuous. So we might opt on the inside of the ERM principle of the empirical risk minimization procedure to kind of approximate that loss function with something that's a bit more well-behaved mathematically. So for example, we might use the L2 loss function here. In other instances, maybe we would use such an exotic loss function that not even an implementation exists in combination with our machine learning training algorithm that we would like to use. This changes nowadays a bit, so especially with modern deep learning toolkits and so on, but still in such cases, the outer loss function might be so exotic that we can't easily push it down inside of the training algorithm. Here's a very, very simple kind of well-known example. So maybe we want to fit a linear binary classifier, so something like a logistic regression, but actually very often we would like to evaluate these binary classifiers with a number of misclassified examples. So percentage of misclassified examples, so something like the 0-1 loss. And the 0-1 loss as a loss function I've plotted here on the right hand side, and you can directly see this is neither differentiable nor actually continuous. So in a certain sense that that creates kind of a discrete optimization problem for me in empirical risk minimization. And I could actually show formally that that the resulting optimization problem just for this class of linear models together with the 0-1 loss actually becomes NP-hard. So in such a case, we'll usually not try to solve such an NP-hard problem, but we rather use a more well-behaved inner loss function. So we could, for example, use the binomial loss, and then we would have really resorted to a logistic regression or something else. I don't know, hinge loss for a support vector machine, or I don't know, a squared loss or something else. But the good news is for evaluation, all of these requirements are really not there, so we don't really have to differentiate things during evaluation because we're not really going to optimize something here, and except for when we are going to tune our model in hyperparameter optimization, which we'll discuss in a different section and not here. In such cases, we very often then use black box optimization, so we still do not require differentiability. Somewhat technical slide here on set-based performance metrics. So I've used the notation actually already on the slide before. So this rho guy here, what is that? So sometimes for certain performance metrics, they are not directly defined on single observations. So there are cases, for example, you will see in later sections the definition of the AUC, so the area under the curve. You might actually define that on single observations, but it's a lot less, standard. Let's put it like that. And there are also other metrics in survival analysis. In general, there might be metrics that are only defined per a complete set of test examples. So in order to cover these cases as well, I'll now assume that the most general object we'll handle in ML evaluation is such a performance metric rho. And this measures the quality of predictions as a scalar for a test set. So it will transform a given vector of, so let's assume we are given some form of a test set, and that test set has actually m examples. And we will now collect true labels, all m true labels for that test set in one vector, bold y. And we'll also collect all predictions for the m element test set in that matrix capital F here. So if our model simply produces scalar outputs, then this guy here will simply be a vector. If our model actually produces G outputs, so G scores for a multi-class classifier or something like that, then it will be, this capital F will really be a matrix in M times G matrix. So M rows for M test examples and potentially G columns for the G score outputs of my machine learning model. And I can now easily see that this rho function here is a simple generalization of my pointwise losses. So if I have a pointwise loss function and would like to use that for evaluation, and I would like to kind of extend that to such a performance metric rho or rho of L, well, I can easily define that as the average of the losses over the complete test data set. So pretty simple. So until now, we have only discussed this generalization error of a fixed model. I've already said that this basically only directly works if we are given a dedicated test set, and that is usually not available in practice. So we somehow have to work with our complete data set, and this actually produces a somewhat weird situation in machine learning, which is sometimes confusing to new students, or also sometimes even confusing, I guess, to practitioners with a few years of experience. So I'd rather try to explain this here slowly, so you really you really get the difference and understand what I'm talking about. So because this is quite subtle, but this is important for understanding what really goes on in ML evaluation, and where many of the difficulties actually stem from. So as I've already said, usually we're given one data set, 1,000 observations, and this is all we have, and this is especially all we have for model fitting and for model evaluation. Now, unfortunately, what we are practically simply going to do at the end is we are going to run one certain machine learning algorithm. So after we have reasoned about what model we are going to use, which hyperparameters we are going to use, I don't know, what pre-processing we are going to use, at some point we'll have defined our ML modeling procedure, our inducing algorithm, maybe our ML pipeline, whatever that is. And we'll run that on that complete data set, because we want to use every data point available to us to produce the best model that we can. We're not going to leave some data points out, right? Although we might use them in a certain way for evaluation. Now, this model is the one we're going to store. This is the model that we're going to deploy and use, and so on. So this model f hat, and this model will then be on the complete data set of 1,000 points. The problem is the following. If we do that, and we are going to create this guy here, in the end, we already now know that there is no data left to evaluate this model in a clean fashion. For non-parametric, non-linear models, the only thing we basically trust in for generalization error estimation is unseen test data. There is zero unseen test data now left for this specific model f hat here. So we can never really compute and apply this GE for a fixed model. Because this dedicated test set is not available to us, there is no test data left. The unfortunate reality now is that we want to reason about the future performance of this model here, and we're going to construct a statistical estimator for its performance. But during the construction of the estimator, we can't really use that exactly this model here. This is what we would really like to do. We would kind of push data through that model, evaluate their losses and so on, but we can't do that. So we now have to kind of do the next best thing. So we have to define something else which might still allow us to estimate the future predictive performance of this guy here. So we're now going to measure the generalization error of the inducing algorithm when we fit that inducing algorithm on data from the same distribution with nearly the same number of points. So instead of reasoning about this guy here, we will now reason about the inducer when we apply that to training data from the same data generating process. So something very, very similar that this guy was constructed on with nearly the same amount of training data. So the nearly comes from, because if I would use exactly the same amount of training data, so if I would use 1,000 points, again, and no points for testing would be left. So if I use somewhat less points, there is something left. And I can use that now as test data for that resulting model here and estimate its future performance in a clean fashion on unseen, untouched test data. So in terms of a formal definition, what I now want to do is I want to construct the generalization error concept, a given inducing algorithm, a certain hyperparameter configuration of that algorithm for a given fixed amount of training data points and train, and a certain performance metric rho. And I will define this here as on the right hand side. So I will now take the expectation over all training data sets of size n train and over all test data sets of size n test. and I will run my inducing algorithm on such a random training data set of size and train, evaluate my performance metric rho regarding the resulting model f hat here on that sampled test data set d test with the performance metric rho. And unfortunately, to make this very proper now, I still have to let this size of the test data set go to infinity, because some of these performance metrics actually might only converge if they are fed infinitely large test data sets. But that's kind of a more technical thing, so maybe disregard this here for a moment, and I'll also show you a simpler definition without the rho in a few seconds. So the important difference now between this guy and the thing that we have seen before is that for this situation here, we're only taking the expectation over our fresh data point xy. For this guy here, we are now taking the expectation over all training data sets, so we are also capturing the randomness and the stochasticity of the learning algorithm, which is probably a good thing, because the training data set is also just simply a random variable, and just simply because we are given a certain data set in practice at hand, that's not, complete reality. That's just a sample from reality, a stochastic sample. So we are capturing that stochasticity here as well, and the randomness of the test data set or test sample. And as we will later on see in the simpler definition there, we can kind of reduce this here to a single test example xy when we use the simpler form of the rho function simply as a loss function. And this property here, this guy, is basically what is estimated by all of the resampling procedures like cross-validation and like holdout splitting that we will study later on. So all of these procedures will produce practical estimators for this guy here. And in a certain sense, we will then kind of make a leap of faith and say that, well, if I can estimate my generalization error for my inducing algorithm for 900 points sampled from my data generating process, I can kind of identify this with the model that I have fitted on data from the same distribution or with slightly more data from the same distribution. So kind of make that small leap of faith. And every model that is now produced during such a resampling procedure is basically an intermediate result, something that we are going to throw away simply to get our hands on this number here that captures the future performance of that hopefully captures the future performance of our given model f hat. It's a single number, but it's an important number. And we can already now see a potential source of statistical problem in that estimator. So that estimator that we're going to construct here will always be what we call pessimistically biased. So we'll actually look worse to a certain extent than our model f hat, our final model f hat, is going to score on future data. Why? This pessimistic bias is in there by construction because this n-train number, so the number of training data that we are estimating for, will always be a bit less. So at least one less. So if you would be willing to evaluate on one test data point, and that's actually possible, as we will see later on for leave one out cross-validation, but it will always be less than the size of our complete data set D, because at least one example needs to be left so we can use that as an untouched test observation to evaluate our model. What we can also do is we can, so this you might find this definition here a little bit cumbersome because of this performance metric rho, and here we have to then work with these complete test data sets. So if you want to have a simpler definition, which is absolutely acceptable, to work with that instead, you can simply define here the generalization error with respect to an outer loss function, L. And in that case, all of that kind of reduces to this guy here. So again, we take the expectation both over the training set and now this one single fresh random test sample x and y. So you can now really see that this is the expected loss of our inducing algorithm when we train that on a training data set of size and train. So actually what I should probably say here, and I would have kind of forgotten, is that this is important. So these D-trains, I've said it here, but I've forgotten it here. These D-train training data sets, they all have to be of size and train, okay? Two random variables in here. It's kind of a large random vector. and this is a single random vector, x, y. And I'm integrating out over both of them in the expectation. I can also, if I want to now kind of retcon the GE of my model and kind of see this as a special case for a special instance of the GE of my learning algorithm when I simply condition on my training data set. So this is pretty easy to see. So we can now, actually, it shouldn't be like that. So it's not defined as, well, I could define it like that, but it's the GE of my model f hat for a given loss function is now the same as the GE of my learning algorithm when I condition on detrain. The reason for that is if I condition on detrain, my inducer will produce that model f hat here. So I have to identify these two guys with each other, and I also have to identify the entrain with the size of detrain, and then the two are exactly the same. Can easily check that by comparing this. Let's use this simpler definition here with with this guy. So if I condition on detrain, this here will simply be fixed, and become f hat. And then I will simply average over the fresh test sample x and y, and both are the same.